Okay, so now we're going to look at kind of an example. We're going to set it up. We're going to set the problem up in a very similar way to how we're going to set up all of the problems. And like I said, I'm going to set up all of the first order equations basically like this. This is a good setup to do the analysis. As we look at more complicated problems, the analysis will get more complicated. But I think this is the best way to analyze the problems if we just kind of do this the same way every time. So the first thing that we want to do is we want to write down the characteristic differential equations. Okay, and even before that, I'm going to look at the PDE and see what's going on here. So we have 1 times the partial derivative of u with respect to x plus 4 times the partial derivative of u with respect to y. And we know that u of x0 is equal to 1 plus x. So in other words, we know what u is along the x-axis. Okay, and we call that the Cauchy data. And I'll say a little bit more about that later on. But we call this the Cauchy data. We call this right here the Cauchy data. Okay, it's a curve. The curve is the x-axis, and the values of the function is given by 1 plus x. Okay, now the system of equations, x dot of s is always going to be what's multiplying the x derivative of u, which in this case is 1. Y dot of s is always going to be whatever is multiplying the y derivative of u, which in this case is 4. In more complicated problems, these will be more complicated, but for now, the thing multiplying the y derivative of u is 4. And then finally, z dot of s. So I didn't say this here. So z of s is always going to be equal to, so let me do a little derivation here. So we won't do this for the upcoming problems, but z of s is always going to be u of x of s, y of s. And so z dot of s, using the multidimensional chain rule, this is going to be x dot of s times the partial derivative of u with respect to x plus y dot of s times the partial derivative of y with respect to u. And remember, x dot of s is always going to be the thing that's multiplying by the partial derivative of u with respect to x in the PDE. So I know that's going to be 1 in this case. And then y dot of s is always going to be the coefficient on the partial derivative of u with respect to y. So this is going to be plus 4 times the partial derivative of u with respect to y. And if u is a solution to the PDE, then this says that this is equal to 0. So z dot of s is equal to 0. Okay. And that's always what's going to happen. The z dot of s is always going to be equal. So z dot of s is always going to be equal to like this part of the PDE. And we'll be a little more clear about what this part of the PDE means in upcoming videos. Let me erase all of this. Okay. Now for the initial conditions for the characteristic equations. So the x and y initial condition, it needs to lie on this Cauchy curve, on the curve along which we are given the Cauchy data, which in this case is the x-axis. So like if this is a typical point, it's going to be x naught 0. This will be x naught, and then this will be 0. And z of 0, well, z of, remember, let me rewrite it down here. Z of s is equal to u of x of s, y of s. So then z of 0 is going to be u of x naught 0, because if I plug in 0 to x of s, I get x naught. That's what this says. If I plug in 0 to y of y of s, I'm going to get 0. That's what that says. But u of x naught, I can use my condition here, my Cauchy data here. This is equal to 1 plus x naught. So this is 1 plus x naught. Okay, and now this is a system of ordinary differential equations. It's ordinary differential equations because the only independent variable is s. And now I want to solve this system of differential equations and use that to help us determine what the solution to the PDE is. So I'm just going to take this as a typical characteristic. So I'm going to go over 1, up 1, 2, 3, 4. This will be a typical characteristic. And I want to get the parameterization for this characteristic. I know it's a line. Sometimes we actually have to solve this before we see what the shape is. But notice, again, like with the previous problem, x dot of s is equal to 1. So this tells me that x of s is going to be equal to s plus x naught. Y of s is going to be equal to 4s. And now z dot of s is equal to 0. So that solution is going to be easy. Z of s is just going to be equal to 1 plus x naught. Okay, so what is this saying? So let me take just a generic point. This is going to be AB is a generic point in the plane. What this says is that U evaluated at this point AB. If I want to know what that is, I just sort of trace this characteristic back to the x-axis, and it's going to be 1 plus x naught for whatever value this x naught is. So U of AB is going to be equal to 1 plus x naught. But this doesn't really work out because I've got a and b over here, but I don't have a and b over here. So what I need to do is I need to figure out how to write this. I need to write this in terms of a and b. So how can I do that? Well, I know that my curve starts here. When s is equal to 0, the curve starts here. And as s increases, it travels along the curve up this way. So in other words, I know A is equal to S plus X naught. I know B is equal to 4S. So therefore, this tells me that S is equal to B over 4. Okay, so what does this tell me? S is equal to B over 4. So this is B over 4 plus X naught. So I don't know why I did an arrow. That's just equals. These two things are actually equal. And so this tells me that x naught is equal to A minus B over 4. So U of AB, and again, AB is just a generic point in the plane. U of AB is equal to 1 plus x naught, and x naught is A minus B over 4. Of course, we want to write things in terms of x and y because that's the traditional coordinate system. And so just I'm going to write wherever I see an A, I'm going to put an x. Wherever I see a B, I'm going to put a y. Because again, AB is just a generic point in the plane. So this is 1 plus x minus y over 4. Okay, now as an exercise, show that this solution, show that this satisfies or solves, I'll put solves, show that it solves the problem. In other words, you need to show that it solves this PDE and that when you plug in y is equal to 0, u of x0 is equal to 1 plus x. Okay, we're going to be looking at more examples, and I hope that will just make some of this stuff sink in even better.